Welcome everyone to the Global Water Futures Core Modeling and Forecasting Teams webinar. My name is Praveen Rokaya. I'm the Science Coordinator of the Core Modeling and Forecasting team. It is our pleasure to present today a webinar on error compensation in climate models. Today we have Dr. Alejandro De Luca from the University of Quebec at Montreal with us. Dr. De Luca completed a PhD in atmospheric sciences in 2011 and since then was a postdoc at École Polytechnique in France and then in Australia. Before joining the University of Quebec at Montreal as an assistant professor, he was a lecturer at the University of New South Wales in Australia. Dr. De Luca research revolves around the use of very high resolution models, their evaluation and their use to better understand local climate extremes, which I believe he will be highlighting today. Without taking much time, I want to kick off this webinar by thanking Dr. De Luca for graciously accepting our invitation to present in this webinar series. The webinar today would be about 45 minutes of presentation, followed by 15 minutes of question and answer session. Dr. De Luca, the floor is yours.
Thanks so much, Praveen, for the introduction. Good morning and good afternoon, everyone. Thanks for joining. So I'm going to be talking about error compensation in climate models. Basically, I will go through a very brief introduction, what we are going to look at in the seminar, and then I will go into some detail into examples of the application of compensation of errors. One example that looks at errors in simulated temperature extremes using CEMIP 5 and CEMIP 6 models, and the other that looks at errors in simulated sub-daily rainfall fields, 3-hourly rainfall, using very high resolution models, including convection permitting models. And then I'll finish with a few concluding remarks, and hopefully we can have some discussion and questions after that. So why and how do we evaluate models? First of all, why? And in fact, the answer to both of these questions depends a little on what are we going to use the model for, and that changes for different researchers. Often what we would like is to have an idea of how much confidence do we have in climate models and how much we can trust them, for example, to look at projections of future climate changes. But for example, those that work on weather forecasting might want to improve the models so they can have a better forecast. So depends a little on the application. The how, it's even more varied, and nowadays what we use often as the framework to evaluate models is the concept of fit for purpose or adequacy for purpose of climate models, where we don't try to answer whether a model is good or bad, but what we try to answer is whether the model is able to simulate what we are interested in and how well can simulate that. Overall, there are many different ways we can evaluate models, but there are a few challenges that are common or appear most of the time. And I listed here some of those challenges. The first one is that we often lack a reference to evaluate the climate model output. So we don't really know what is the truth and what we can use to compare these climate models. Of course, this depends on what are we trying to evaluate. Some variables might be better observed than others, but this is often the case, and it is more often now than that we sometimes run very high resolution models where data observations at very fine scales are not available. A second problem is the lack of a clear definition of what we mean by what is a good representation, not just a good model, but what does it mean that the model does well something. And in fact, there is no, again, this is a very arbitrary threshold that kind of everyone can choose. And everyone or many of us will probably already wrote in a paper, the model simulates reasonably well something. And this reasonably well, in fact, is it's quite arbitrary, and it depends on what do I think that's reasonable. Maybe someone else might disagree on what's reasonable. So there are clear some issues with that too. And then there is another one, that is that what we evaluate, there is a lack of knowledge about what are the key or the critical processes, which eventually, when we try to evaluate the process, eventually we need to come up with some metric to evaluate that process. And is that whether that process or that metric we come up with really tell us something about what was the overall purpose of the research. So for example, we often evaluate very complex processes. For example, precipitation is a very, very complex process that depends on a range of phenomena, different scales interacting with each other, etc. And when we have an error in precipitation, to identify the source of the error, it's really, really hard. And so the metric we construct to tell something about the errors in precipitation might reflect some processes inside or might not. And this is what I will focus a little, and I hope if it's not very clear what I'm gonna do, I think it might become a little clearer as the presentation goes on. So I start first of all with one example. We are gonna look at errors in simulated temperature extremes using semi-type models, 5 and 6. This is a time series of daily maximum temperature. In fact, it's a synthetic time series. It's not simulated, or, well, it's simulated by the very simple algorithm. What we have is temperature as a function of time, and we have 20-year daily data. And of course, in those 20-year daily data, you can identify at some point there is a maximum temperature over the whole period. Of course, there is a minimum temperature too. And what is clear is that when we evaluate how well, for example, a maximum temperature, the extreme temperature happen, what we can see is that it will depend on quite a few things. For example, the value that we obtain here on the top will be a function of how we represent the amplitude of the annual cycle. And even if we now show the same maximum, but now we show a 225 days time series a little around the maximum, you will see that there is a lot of variability that is not only related with the annual cycle, but comes from other scales. For example, synoptic scale variability, or the fact that we have El Niño and La Niña that will lead to some seasonal years with the seasonal temperature higher than others. So the specific way we get this maximum temperature, it's a quite complex way. And of course, it also depends on how well the model, for example, represents the diurnal cycle, because we are looking at the maximum temperature on a day. And so basically what we can do is to try to express the 20-year absolute maximum temperature as the sum of 4 different terms. One term is related with the mean temperature, which is the calendar day mean temperature. It will vary with the season, for example. Another term, sorry, the first term is the long-term mean temperature. The second term is the long-term diurnal temperature range divided by 2. So the sum of these 2 terms give us the long-term maximum mean temperature. And then there are 2 terms that tell us stuff about the extreme itself. So the extremes is related with the specific conditions of the event. For example, as I said, synoptic or lower frequency variability. And so these 2 terms are the ones that really make the extreme an extreme. And I separated this anomaly compared to the mean long-term mean in 2 components, one that is related with the seasonal variability and another that is related with the synoptic variability. Of course, you can always have a look at a few papers where we explain this a little better. But this is the idea, that the maximum, the extreme, it depends on a few different terms, including some that are related with mean values so we use the whole 20-year period to calculate those, and others that are just specific to the event. And of course, we arbitrarily chose to reflect the 20-year absolute maximum, but we can do exactly the same for the 20-year absolute minimum temperature. And in that case, we will obtain an equation that it's quite an analog. Of course, it's a little different, but has similar terms. And from these two equations, basically, we can derive one single equation for the 20-year absolute maximum that depends on the 20-year absolute minimum temperature, and four different terms that give us different parts of the whole variability between the coldest day that the model simulates or that we observed in some observation and the maximum temperature that we observe in some observation. In some way, what we are saying is that if I now show the same plot as before, but now I show you the minimum temperature here, what we are trying to explain, or this equation tell us, is how we can break the whole variability between the full amplitude of the model in different terms that has some physical meaning. And of course, here with this equation, you can see very well how error compensations might play a role. So, for example, if you evaluate for example, the bias or the absolute value of the bias, which is here defined simply as the absolute value of the sum of all these terms in a given grid point, you can see that you can obtain a relatively low bias by having again, the error in this term can be, we can have a small error in this term by having large positive errors and large negative errors in different of these individual terms. In particular, we can have 0 by having very, very large errors in the minimum temperature and very large errors in the amplitude of the temperature, the annual temperature range, or the diurnal temperature range, or the seasonal anomaly term, or the synoptic anomaly term. So the idea is to define a new error that I call here, and I will call it in the other example too, the same way as the additive absolute error. Instead of, it's very simple, instead of summing, calculating the absolute value of the bias, what we sum is the absolute values of the individual terms. So in that case, this AAE, it will be 0 only in the case that the error in all individual terms, in each of these individual terms, is 0. And so in some way, this error metric does not allow to have error compensation inside inside the error metric. So what we do is basically I apply this decomposition to 5 observational products, BEST, had GH-CND, CPC, and 2 reanalysis, ERA 5 and ERA interim. And then we apply it to 37 SEMIP5 and 28 SEMIP6 models. And we do that for this period, 1986-2005. And so what I show you here is the 37 SEMIP5 models, the absolute error. So basically the absolute value of the mean bias for each of the models at the global scale. And what we see is, well, that errors are on average about 3 degrees, and they vary between 1.5 or yeah, maybe nearly 1, let's say, until up to almost 6 degrees. You can identify a few models that look like, for example, pretty bad. The CESM FastChem has the largest error, and it's about nearly 6 degrees. And you can also, of course, see some models that seems to do pretty well. And this F-Goals model has an error which is one of the lowest, about 1 degree. And so you can ask the question: is this gold? what we are seeing here is this the best model we can use to evaluate or to assess temperature extremes. And so we can do exactly the same and now calculate the additive absolute error. And in fact, the rank of the models, so the order in which they are ranked, it's exactly the same in both of the figures. In fact, I have ranked the models according to the an increasing error, absolute additive error. So of course, the models here have a very low absolute additive error and increases towards the maximum here. And what you see is, first of all, for example, if you consider now the CESM FastChem model, it looked like in terms of the absolute additive error, so the one that in principle does not allow to compensate errors, it's an average model, better than average model. And if you look at the other model that looked like one of the best models, this F-Walls model, in fact, it appears that it's a pretty poor model. It's not the worst, but close to top 5 worst models according to this error. What this is saying is that the bias here was obtained by compensating errors of different sign according to the decomposition we showed before. You can see here too that additive absolute errors are always higher than absolute errors. That's the way the metric is constructed. And you can also see that we can obtain similar values of the full error, so the sum, by having errors that are somewhat different for individual components. I'm not going to go much in the details, but that is roughly what we see here. And so the question is this gold? It seems to me that the answer it will be no, clearly will be no, because in fact, we are getting the right response for the wrong reasons. And that's a little what we are trying to avoid with the new error metric. We can use the error metric to do, of course, to look at other things, not just the errors across models, but for example, errors across regions. And here I show these are the some regional different regions, and we show average errors across these different regions there. And again, I have ranked the regions according to their additive absolute error. And what you can see is that, for example, consider the Amazon region, AMZ region. It has an absolute error that is relatively large, one of the largest on the order of 3.5 degrees. And however, it has one of the lowest additive absolute errors. In fact, if you look at this, the additive absolute errors are relatively low for regions that are close to the tropics, and they get much larger for extratropics or high latitude regions. The reason being that the variability and the chances of getting wrong those regions in extratropics or high latitudes are much higher. And you can also look at, for example, TIB, which is the Tibetan Plateau region, which is a very complex region to simulate. And in the absolute error, it appears as relatively good, the order of 2 degrees error. However, when you look at the absolute additive error, in this case is about 15 degrees, and it seems the hardest region to represent, which also in some way makes sense. Again, the way different regions or different terms play a different role in different regions. And I'm not going to get much into the detail of that, but again, the papers show some more detail on this. Just to finish this part, what I show here is one error as a function of the other. So in the x-axis, you have the absolute error, and in the y-axis, you have the additive absolute errors. Again, the way it's constructed, we know that AAE is always larger than AE, so it could be equal if all terms are 0 but 1. But in fact, it appears that no data set show showed this. So we always find models that are blue or observations or reanalysis. So we choose one observation as the reference, and so we calculate the difference also compared to other observations to get an idea of what's the observational uncertainty. So the red dots give us an idea of the observational uncertainty. The blue are the errors of the models themselves. Again, what you see is we are always above the 1-to-1 line. And again, that's because AAE is always larger than AE. But what you see, and I think this is a very interesting point, is that if you consider the absolute error, you have the difference between, for example, the observation best and the HAD GCHD that has been chosen as the reference is much larger. It's often larger than the difference between models and the reference. That is, there are 22 models out of 31, and in this case it's not 37 because I'm using an earlier study that we only had 31 models. So 22 models out of 31 that are within the observational uncertainty if the metric we use is the absolute error. However, if we use the additive absolute error, there are only 2 models that are within the observational uncertainty. What this is saying is that observations can be quite different if we only look at the left-hand side of the equation. But if we ask to represent individual terms well, in fact, the observations, they agree quite well on what they say. In fact, models have a much harder time to simulate well AAE, compared to AE. I'll come back to this in the other example too. So now I move to the second example, and here we are going to look at errors in simulated subdaily rainfall fields using very high resolution models. And the idea, it's in some way is the same. What we are going to do is that, okay, now we want to look at the precipitation. Not really extremes, just precipitation in general. And what we are going to try to do is that the precipitation field is going to be broken up in different terms. And we will eventually use those terms again in the similar way we've done before to define a new error that asks not to simulate well the left-hand side of the equation, but to simulate well the different terms that lead to the left-hand side of the equation. And to start that, we assume that the precipitation, the total precipitation, for example, is in some way a function of 2 larger scale variables. One larger scale variable that is omega, is the pressure vertical velocity at 500 hectopascals. And the other larger scale variable that is, we call it here W, and it's the vertically integrated water vapor. So we chose one dynamical variable and one thermodynamical variable. I changed a little the notation, but it's exactly the same. And I added LS because we smooth a little both variables, so they represent the larger scale and not at the grid point level. The idea is that the dependence is then assessed by binning both of these variables into different, what we call regimes, thermodynamical and dynamical regimes. And so, for example, in a given region, or could be for a given grid point, you can bin in terms of omega and in terms of vertically integrated water vapor, and we can put in each bin the total precipitation that we obtain. And so, for example, this is based on I merge 3-hourly data just as an example. What we get is that the largest amount of precipitation for this specific region is falling at omegas that are around minus 0.4 Pascal per second, and with some integrated water vapor of the order of 28 millimeters. But we go a little further, and for each regime, in fact, we separate the precipitation according to the classic and quite traditional intensity and frequency decomposition. So if we do that for each regime, we can express the total precipitation according to the total number of events occurring in that regime, IG, the probability that we found a precipitating event in that specific regime, and the mean intensity of the rainfall whenever that the rainfall happens. And basically is the total precipitation in a regime IG can be approximated as the product of, again, n total number of occurrences in that bin. P is the probability of having precipitation in the bin, and E rain is the mean intensity of the rain. And if we show this, what we obtain, for example, again, using the iMerge 3-hourly data, this is the same graph as I showed before, total precipitation for different regimes. And then it is obtained as the product of these three different terms. The total number of events, which are, you can see that the number of events, most of the time we have omega that is close to 0. So most of the occurrences are around omega zeros and with a integrated water vapor of the order of 15. And then you can see that this term that corresponds to, I call it here, the triggering of precipitation, it's very low, it's nearly 0 when the movement is upwards, or the movement, the larger scale movement, the larger scale vertical movement is very small. And as the omega goes to larger, more negative values, the movement is upwards, and then the probability increases. And for omegas that are lower than -4, we always get precipitation. This is what this term is telling us. And the last term is telling us whether what's the intensity of the rainfall whenever the rainfall, an event occurs in each of the regimes. And of course, as we might imagine, the intensity increases as we move towards higher humidity contents environments, and we move towards environments where the larger scale omega vertical velocity is higher. And we go from values, well, of the order of 1 here, 1 millimeter every 3 hours, to values of the order of 100 millimeters per hour. So the idea is that we can, again, apply this decomposition to observed data sets and model data sets, and we can calculate an error. And so if you do that for the model part and for the observations, M and O, the error, of course, is the difference between these two. And we can play a little with these different products or basically we do a Taylor approximation, and you can get the full error is equal to the sum of these 4 different terms. And the 3 first terms are pretty trivial. So one tell us what's the error in the occurrence of the different regimes. The second tell us what's the error whenever we are in that regime. What is the error that maybe the model will produce rainfall more often than the observations, or the other way around. And the third term tell us if our intensity, whenever it rains, our intensity is right or not. And then there is also some residual, in fact, the second order products and third order products that are merged in this term that I call the residual term, R, which is often small, although not fully negligible, but at most 10% more or less. So we will focus on the results of these three terms that we know well how to interpret. And I will call, so basically what we get is that the total error in precipitation is given by an error that is related with how well the model reproduces the environment where the rainfall might occur. Another error that is related with how often, or whether too often or not too often, the precipitation is made, and what's the intensity. And as before, we will basically apply this as the decomposition, the full decomposition, to several observed data sets and several simulations. So in terms of observations, we use always ERA5 reanalysis to get omega and the integrated water vapor. And we use 5 different satellite-based precipitation products to estimate the rainfall terms. And among those, we have the CMORPH, we have iMerge, GSMAP, MSWEP, and TRIM. And what we evaluate is this ensemble of 330 simulations, where the full ensemble is produced by using 3 different resolutions. So we have a triple nesting approach. We have the WRF, a domain that is run at 24-kilometer grid spacing, and that covers, in fact, it's the Cordex Australasia domain, includes all Australasia. And then we have a second nesting at 8 kilometers that you can see there in the figure, and we have a 2-kilometer nesting inside the WRF 8. And of course, the comparison among all the data sets is going to be made in a domain that is included in all 3 simulations. And then for each of those, we also run a 5 multi-physics ensemble. We use the WRF model, and we change one at a time different the representation of different subgrid scale processes. So for example, we'll use a different cumulus scheme, different microphysics, PBL, and radiation schemes, one at a time. So we can see what's the difference that those include. And basically with that different configurations, we simulate 11 events that were chosen as because that were cyclones that arrived in the eastern coast of Australia. In fact, they are called East Coast lows, similar to the East Coast lows we get here in North America over the Gulf Stream. We get also East Coast lows in the eastern part of Australia. And in fact, we chose some of these extreme East Coast lows that happened in the last 15 years, and 11 of those. And basically, we simulate all those 11 events. In addition, we also include 2 different boundary conditions at the surface, where we use especially smooth SST and some SST with a high resolution SST data. But that leads to relatively small differences, so I'm not going to really discuss that. In any ways, we have in total about 6 years of simulations. Again, WRF2, so it's run in convection permitting mode, so the convection is explicitly represented, and we turn off the deep convection scheme. And here in the right, you see just one of the examples. This is the 2016 event that in fact led to a lot of damage in Sydney. And you see the mean sea level pressure in black contours, and then you see the colors show the rainfall rate in millimeters every 3 hours, also coming from iMerge. So we applied the decomposition to each of these simulations, and of course, then we can calculate the errors in the way I show in the equations before. And so the total precipitation here I show just for one specific simulation. This is the WRF2, so one of the convection permitting simulations. CTL is the control simulation, and what you see is the total precipitation error as the sum of the three different terms that I defined before. Well, clearly you see here quite quickly the interest of applying such a decomposition, in the sense that you have positive errors and you also have negative errors. So again, if you calculate the mean of this, in fact, well, in this specific case, we get a little a negative bias in the total precipitation, but the error is much smaller because, again, we compensate among positive and negative errors, much smaller than what you could get using the absolute error. And what we see is that in terms of the environment error, we get some negative errors for low vertical integrated water vapor, and positive errors for high vertical integrated water vapor. Basically, what this is telling us is that the WRF has a bias in the has an error in the vertical integrated water vapor, where too often has too much humidity. And then if we look at, for example, the precipitation frequency error, what we see is that we produce precipitation way too often for relatively low dynamical and thermodynamical regimes. Whenever omega is nearly zero, we tend to produce rainfall when it seems it's not observed. And then we kind of have some compensation related to that, because whenever we produce rain, in fact, the intensity is relatively low. So without, again, I'm not gonna go in much detail. In fact, a little as I did with the other example, but again, we can define a new error metric. So for example, you can calculate, as we did before, the absolute error. That is simply we sum over all terms and we calculate the absolute value of that, which is the absolute value of the mean bias. And again, you can do as we did before, calculate a new additive absolute error, where the sum is of the absolute values of each of these terms we see there. 3 different terms, but also all the different regimes. And in fact, you can play a little with that, and you can combine in different ways, or to assess the degree of error compensation. In any ways, the AAE, again, does not allow for error compensation, and AE allows for the full compensation of errors. We can, if we are interested in, for example, model development, and we want to know which specific configuration seems to produce the best results, we could look at this kind of plots. So for example, here we separated the analysis in land grid points and ocean grid points, because the behavior is quite different in both. And then what you see, it's a pretty busy and messy figures, but they include all the different members in each of the plots. And instead of showing the 2D map as we did before, what we have done is that we define weak omega LS and strong dynamical environments. And we do we show the error as a function of vertical integrated water vapor. So we have on the left, we have for weak dynamical conditions, and on the right for strong dynamical conditions. And then you have that the total error is the sum of the environment, the frequency, and the intensity. And you can go and look, okay, what's going on, yeah. For example, here you see these greens with circles, which is the simulation run with a different planetary boundary layer scheme, seems to produce, for example, better results in this specific case compared to the control, etc., etc. Again, not going much into the details, but there's quite a few of physical insights that we can get from this. But I come back to the absolute error and the additive absolute error. And here, as before, I show the additive absolute error as a function of the absolute error for the different simulations. And again, we also include differences between observations. In this case, what we use as the reference is not one observation, but we use as the reference the median across the different observations. And so this here give us again an idea of what's the observational uncertainty. And as before, if you look at the observational uncertainty in terms of the absolute error, so the x-axis, you see that, for example, when considering the dataset iMerge here, quite a few, about half of the simulations tend to produce an error that is within the difference between iMerge and the median across observations. If you consider the additive absolute error, there is none of the simulations that is within the observational uncertainty. This is very similar to what we found before. You can also calculate some kind of correlation to see whether the sensitivity of one error is similar to the other one. And here I show the value of the Spearman correlation, which in this case is 0.48, which is not completely negligible, but certainly not very high. And in fact, that's visually very clear that there is not a lot of correlation between the errors in the absolute errors and the additive absolute errors. You can do that for ocean, as I was showing before, and of course you can do that also for land grid points. In fact, for land grid points, this sensitivity it's completely different. But again, what we obtain as before is that using the absolute error, most models are within the observational uncertainty, but using the additive absolute errors, in fact, in this case, with the exception of the TRIM, the triangle towards the right is the TRIM dataset. With the exception of the TRIM, all models are way above the observational uncertainty. In fact, this tells us that for some reason, and in land grid points, at least over this region in Australia, in Eastern Australia, TRIM seems to do some things quite different compared to the other observed datasets. And we can also try to produce some figures that show us the overall results by fixing different aspects of the ensemble. So for example, what I show here is a additive absolute error for all the simulations that were done using the WRF-24, all the simulations done with the WRF-8, so 24 kilometers, 8 kilometers, and 2 kilometers. And this, on the left, you have the ocean, on the right, you have the land. And of course, then you have how from the total error is separated according to the different terms. And the values you see inside each of the boxes, in fact, are the relative differences compared to, in this case, the WRF-24. What this means is, if these numbers are positive, it means that the error is higher, 8% higher, it's in percent. And if it's negative, clearly it's because the error is lower. So what we see is that overall, the WRF, for example, in the ocean, WRF-8 WRF at 8 kilometers improves the overall errors by 1%. But if we use the convection permitting version, it improves by about 20%. And if we look at land grid points, in fact, the WRF-8 deteriorates compared to the WRF-24. And what we see is that the WRF-2 still improves compared to the WRF-24 by about also 20%. And in fact, it does it by basically improving all three terms, which is also quite nice in both cases, although the terms that are improved are not necessarily the same. For example, over land, it seems that a lot of the improvement is coming from the probability, so the frequency of the rain, but this frequency doesn't seem to play a role over the ocean. The red lines, so the dashed and the full lines, in fact, show us how large is the observational uncertainty. Again, all the errors in models are way above the observational uncertainty over ocean. And here, in fact, that I included the full range of the full uncertainty, or the uncertainty calculated using only 4 of the 5 observational data sets, just to exclude TRIM. And you see, well, that drops quite a lot. We can do, of course, the same, but instead of fixing the resolution, we can fix one physical scheme. So, for example, we can compare the control compared to what we obtain when using another PBL scheme, another microphysics, another radiation, another cumulus, exactly. And sometimes differences are quite large. They could be as large as 10%. So I will now conclude, and I think I am pretty good in terms of the 45 minutes that was allowed. Conclusions, first, the skill of models clearly depends on the error metric used. In some way, when we evaluate, we should try to reflect what are we use the model for, and try to evaluate the model so it reflects in some way this. And so basically answering the question whether the model is fit for the purpose we want to use it. The more we break up the errors into physically meaningful and coherent components, the harder it is for the models to get the right results for the wrong reasons. So if we only calculate a bias of a relatively complex process, it's likely that we can get the right low bias, but doing things quite wrongly. If we ask to make different components well, then the chances of getting a low error are much lower. That's a little what I was trying to say there. In climate change studies, for example, a key, something that we would like to learn when we evaluate the models is whether our model has some good predictive power. And this is another question, but I think it's relevant, although I haven't addressed it in any way here, but is still remaining the question of whether the error metric we are using tell us something about the climate change, at least for those we are looking at changes in the climate. And I think there's quite a lot of stuff to do regarding that question. So I leave it there, and I hope you have some questions and comments, and yeah, thank you.
Thank you, Alejandro. That was really fantastic talk. We'll be now moving to the question and answer session. I don't immediately see any question now, but I believe the questions will be trickling now. Yeah, I'm thinking from, it's not a specific question to your talk, but just thinking from perspective of a hydrologist, like a lot of time we want to use this climate data for our models, but we don't go into too much detail, of knowing, the errors in the models are for the right reasons or not. So for such situations, what advice do you give for other hydrologists that are, like, let's say, not the first hand, not delving too much into the climate models, but using the data? So how can we do more due diligence to be aware of these issues?
Yeah, I think I'm not sure I have much advice, but what I can say is that, again, I think a key is that very often what we really are interested are very complex processes that arise from the interaction and from the sum of very different, for example, temporal and spatial scales. And again, this idea that the end result might appear to be relatively good, but maybe we are doing other things very badly. So maybe sometimes we can try to think, how can we break those errors in easier interpretable components, and can we look at those other components individually and see whether we are getting that right result for the right reasons. That's yeah, I think, again, it depends quite a lot on what specific aspect are you looking at and these kind of things. But
yeah, we try to do with our We try to do that with our hierarchical models. We try to see our different processes if they are represented well, but then a lot of time for climate data, we just use whatever is available. We don't go into too much detail. Anyway, there's a question from Jim, and he says, firstly, I really like your analysis, but I think you have to be careful to call your products observational error. They are products and models of great information, isn't that right?
Yes, that's right. They are a mix of. Um, I totally agree. In fact, we still call observations. In fact, of pure observations, we basically don't have pretty much anything that we use to as what used to be observations, because they all have some kind of model. This satellite data, the retrieval, it's originally microwave and infrared information. So we are not observing precipitation. So there already we have an algorithm that will tell us from radiance, will tell us something about precipitation. But then all of these data sets I use are corrected using in situ data. So again, there is a different on the way that those are corrected. And some of them, for example, MSWEP, on the last example, it's also get information from the analysis. So I totally agree. This is in the paper, I think I said often satellite-based products are certainly not pure observations as we used to use maybe 20 years ago. There is, yeah, I agree. Thanks for that comment. Yeah.
Next question is from Chandra, and she's wondering if the error measures that we use can give us confidence on implementing, future projections in terms of correcting the bias based on the errors.
I think personally, I think that I have quite a few good reasons to think that this additive absolute error is better. It tells us more about real errors in models than the bias or the absolute error. But the truth is, for example, I never looked at if there is any relation between this error and future changes, which it can be done and should be done eventually, but I haven't done it. So I cannot say for sure whether that's the case, but I think there are good evidence to think that this is a better metric error than the simple or traditional bias.
And relating to that, there's a question from Mazda, and he's wondering if this error metric can be used also for other models like hierarchical model. What are your thoughts on that?
Yeah, a metric like this can be used for anything. The only thing you need to think about is how to decompose the error in something. And then you can use the decomposition to define this some new error metric that doesn't need to be exactly the way I did it. I did it like that before. But the key is that you need to be able to break the error, the original error in smaller components. And then you will ask the model, okay, you will be good only if you tell me well the individual error. So yeah, if you are able to figure out a way to decompose the error in smaller pieces, then you will be able to apply this kind of methodology.
Thanks. There's another follow-up question from Jim, and he says, sorry if I missed it, but is there a concern that you are comparing over different observed product scales, especially for the probability of rain occurring? And do you consider thresholds on if it has rain or not, minimum threshold?
Again, thanks, Jim. This is a very good question. I didn't go in all the details. I could send you the paper where everything is explained a little better. We did take care of that. So all the comparisons are made at the coarser resolution, which is the 24-kilometer grid of the WRF model. And so the way we upload for example, the WRF 2 or the WRF 8 to the WRF 24 grid is using conservative remapping. So basically, we are taking care of the spatial scale, and then all the data is 3-hourly data. Also, in part because there was one observation data set that was only available every 3 hours. Yeah. So Yeah, sure. Can you please send me an email and I reply with the paper, no problem.
The next question is from Genoa, and this question is, how many members are in each model simulation settings for the precipitation error research? Does the predictability of the weather play a role in the second research regarding the precipitation errors?
Not really, because I like that question too. I mean, we'll certainly if we rerun the ensemble with different initial conditions, we will probably get very small differences. But in fact, we have the full ensemble, the 5 physics and the 3 resolutions, run with 2 different SSTs that only differ on the spatial scale. So one is smooth SST, another is a high resolution SST. And the results we get are very similar. In fact, if I show the last figure where we calculate the overall error with one SST or the other, the difference is 0. What that means is that lots of the error are coming from the physics and the resolution, and that initial conditions, although in the numbers will differ, they don't have a strong impact. Thanks.
This is a comment from Jin that says, I really like to have the paper, a very interesting and difficult analysis to do. There is no perfect answer.
Sure. Yeah, as I said, Jim, just drop an email and I reply with the paper, no problem. It hasn't been published yet, but I can send you the one that is in revision. Yeah.
I'm just wondering, just hypothetically, is it possible to also to look at if the errors are coming from the from physical representation or from the numerical implementation of the model?
Yes, I didn't. I only tested differences between subgrid scale parameterizations. I didn't test any difference in the numerical schemes using the model, but of course it could be tested, no problem. You just need to run the new simulations with the different numerical scheme and compare what errors do you get. Yeah.
Thanks. I don't see any more question. I'll just give everyone.
There's one. Can we use AAE in a hydrological models? I think that was the question before. Yeah.
Yeah. So, but I'll just give few seconds if anybody has any last question.
Sure. And again, if anyone is interested in some specifics, just let me know and I can share some of the papers.
Thanks. Yeah, I don't see any more questions, so we'll be wrapping up today. Thank you, Alejandro, again. And I also want to thank everyone that attended the webinar. The video recording will be available later today in Core Modeling website. Just a note that next week we will be having Dr. Andy Wood from National Center for Atmospheric Research in the United States, who will be providing a webinar entitled Advances in Large Domain Hydrometeorological Modeling and Prediction to Support Water Management. So please stay tuned. That will be all for today. And thank you again. And please stay safe. I wish you all a good day.
Thanks, Praveen. Bye.